Hello everyone. Let us discuss the feature reduction or dimensionality reduction problem in pattern classification. In previous lectures, we saw that high dimensional feature vectors increase the complexity of the classification problem as well as the complexity of error estimation. Also, the visualization of high dimensional feature vectors is not feasible because we cannot visualize feature vectors or data in feature space higher than 3-dimensional space. One approach of coping with the problem of high dimensionality is to reduce the dimensionality by combining the features by using some kind of transformations. Means transformation of feature vector from one feature space to another. But there are some issues like transformation is it can be linear or non-linear, or while we are reducing the feature dimensionality whether the class level are available or not. These two issues need to be taken care while we reduce the dimensionality of feature vectors. Particularly, linear transformation for linear combination of feature vectors are simple to compute and also analytically tractable. That means we can easily deal with linear transformation problem analytically. Linear methods project the high dimensional feature vectors into a lower dimensional feature space. And the advantage of these projection is that the complexity of classification and error estimation will be reduced. Also, the visualization of multivariate feature vectors or data will be possible in 2-dimensional or 3-dimensional feature space. Let us try to understand the objective of dimensionality reduction problem. Say X is d-dimensional feature vector in d-dimensional feature space. So, this is the real space which is the d-dimensional, and here our objective is to find a linear transformation matrix A that will transform the d-dimensional feature vector to d-dash dimensional feature vector y, where d dash is smaller than d. That means transformation matrix A will reduce the dimensionality of feature vector x. So, here our objective is to find the transformation matrix A, and that should be optimal. So, there are the two classical approaches to find the linear transformation matrix. The first approach is the principal component analysis, and the another approach is multiple discriminant analysis. Both the approaches attempt to find a projection of feature vector or data, but the difference is that PCA looks for a projection that best represent the data in a least square sense. However, multiple discriminant analysis seeks a projection that best separate the data in least square sense. So, a very important point can be noted down here that both the approaches project the data in least square sense, but one is best for data representation and another one is best for data separability. So, here it is very simple to conclude that the discriminant analysis consider the class level while finding the projection wherever the class level is not required to compute the projection in case of PCA. Now, let us discuss the principal component analysis to find the projection that best represent the data in feature space without considering the class labels. So, let us consider we have n number of feature vectors in d-dimensional feature space, and we are looking for lower dimensional feature space where reconstruction error of xi is minimized. For now, it may be possible that this statement is not clear to you. Don't worry, as we go through the approach, it will be clear to you. So, let us try to find the projection in least square sense. Suppose that we want to find a vector x0 such that the sum of square distance between x0 and the various feature vector xk is small as possible. So, we define the cost function as this. Here this notation defines the Euclidean norm, or we can say that Euclidean distance. So, here we seek for the value of x0 that minimize j0. We need to minimize this cost function. It is very simple to show that the solution to this problem is given by x0 equal to m, where m is the sample mean, which is given by this expression. Let us verify that optimum value of x0 is the sample mean. So, we have seen that what is the cost function. So, cost function is sum of squared error. So, squared error is this, and we have to take the sum over all the samples. So, we can rewrite this expression as summation over k equal to 1 to n So, here m is a variable and that is the mean of all the samples. Then just we need to square it, we can simplify it. So, the first term it will be x0 minus mean square minus 2 summation over k equal to 1 to n x0 minus mean transpose xk minus mean plus k equal to 1 to n xk minus mean and the square term. So, we can further reduce it to that this term is independent of k. So, we can take out this one. So, we can rewrite k equal to 1 n x0 m. So, minus 2 x0 minus m transpose summation xk minus m k equal to 1 to n plus summation over xk minus m square, where k equal to 1 to n. So, you can look at this term. If you will simplify it, then you will find that this term is 0. So, we can write k equal to 1 to n x0 minus mean. So, you can notice here that this term is basically the independent of x0. Here you can observe that the second term is basically the independent of x0. So, this complete cost function is basically, it can be minimized by choosing x0 as the mean. So, we can say that it is verified that optimum value of x0 is basically the sample mean.